아니요.
프렌치한 스테이는 아니고 아이소는 분리할 수 있는 부분이기 때문에 사람이 인터미디어트에 가까웠고 디텍트도 가능하고 분리도 가능하고 프렌치한 스테이트는 알불씨에 붙은 사진은 하지만 화면에 문제가 없느냐 H7이 중성이고 화면은 마이너스 14.8도 오늘은 마이너스 10도 이게 10도가 이거는 단위가 알 수가 있습니다. 반은 오겐이지만 단 H잖아. 생각을 끄있어 생각적인 걸 하는 대승보라는 이거는 약간 애시드하다 그러고 애시드한 정도가 10 정도 되면 애시드한데요. 제법 애시드 10 정도 되면 1000개 중에서 1개가 프로톤을 내는 겁니다. 제법 애시드 7 정도 되면 진짜 애시드 반전 프로톤을 내놓고 나머지 만드는 겁니다. 상당히 애시드 나이트로 페놀 좀 되면 진짜 애시드가 우리가 말하는 일반적으로 과학에서 말하는 것 중에는 좀 애시드한 거 그걸 치면 페놀 같은 거는 상당히 약한 애시드지 텐이니까 한 4, 5 정도 되면 우리가 제법 애시드한 거 식초 그 정도면 좀 애시드한 거 상당히 애시드한 진짜 애시드한 거는 0, 3 정도 가면 0이나 그보다 더 낮은 거라고 할 수 있죠. 자, 우리가 화학을 그래도 공부했다 보면 조사 일반 학생들 공부했으면 유효하게 문제 조금 어려웠잖아요. 요즘 독학들은 그래서 공부했으면 좋겠지. 그리미아드 레이전트고 메틸 그라니드 레이전트 사이클로 행상 그린하드 레이전트에 물 집어넣으면 그린하드 레이전트 깨진다고 그러죠. 알코올도 마찬가지야. 알코올이 들어서 프로톤 소스가 있으면 그거하고 반응해서 메틸 그린하드 레이전트가 깨져가지고 일어나는 거죠. 원하는 반응은 당연히 아니겠지. 우리가 원하는 반응은 뭔가 펑셔널 그룹을 바꾸고 하는 걸 원할 텐데 싼 기억 만들자고 이런 반응까지는 않을 거예요. 그죠? 10번 뭔데? 사이클 헥사논 너는 이 키톤이고 악세션이 돼야 되는 거죠. 악세션은 아니야. 그래도 시간 충분히 줬어요. 30초. 지금 많이 맞췄네. 좋아. 자, 이것도 뭐지? 지워야 되겠네. 재미삼아 보. 오케이. 자, 그러면 수업을 시작해봅시다. 오케이. 오늘 17과 공부하고 있고요. 다음 주에 그거 한 챕터 더 하고 나면 다음 주에 시험입니다. 첫 번째 시험에서 가까이 다가왔으니까 재미있게 시작하도록 합시다. 자, 오늘 배우는 거는 알파라고 페놀의 지난 시간에 시작했고 오늘은 조금 더 반응을 들어가서 반응에 대해서 공부를 하도록 하겠습니다. 지난 시간에 벤젠 이걸 하려고 했지. In the last class, we talked about this numbering of this the molecule of the benzene, right? And there was two options. One was atomic number or the alphabetical order. So when I checked, looks like it's alphabetical order. And then this one is bromo is the first, chloro, iodide is the second order. So how about this? How do you give this name? It's almost the same molecule. These are isomers. And position is changed, structural isomer. So basically same functional group, just a different position. This is called as a residual isomer. And this is one kind of a structural isomer. How will I give the name? In this case, chromo is still number 1. And we give the name. Same order of alphabetical order, B, C, I, but different number. In your notebook, I give you a little more complicated molecule like this. Now, same way, you could think how you can give the name is a little more complicated, but still bromo is the highest priority because of the alphabetical order, but it doesn't take 1 because you want to minimize the number here. Then your option can be 1, 2, 3, 4 or 1, 2, 3, 4. Then BR becomes 3, so you don't like it. So BR becomes 2, and then you give those numbering. But order is alphabetical order. Okay? So alphabetical order for benzene ring. Then I was thinking, there was some another system. There is atomic number or weight of those atoms. I realized that is for RS system. When we give those RS system, we give those priority 1, 2, 3, 4. Right? Then the priority is highest the atomic number. This is 1, 2, 3, 4. Right? Then depending on this, then using this the orientation, we put the lowest one behind, and here 1, 2, 3. Then it is rotating this way, counterclockwise. That's S4. Right? And then if it goes clockwise, that's what we call alpha. Right? So that stereochemistry we are going to handle until today too. Okay. So this week we are studying about the alcohols. Alcohol is we could make from starting from the hydrocarbon, simple hydrocarbon, and then to handle those molecules. Hydrocarbon is very boring and it has only CH bond. That's why we give some functional group to this. So far we learned only 2 kinds. One was halogen, alkyl halide, right? The other one is oxygen. Then it becomes alcohol. Still, we have a huge variety of molecules. 굉장히 다양한 모lecule을 만들어지잖아요. 레고조 가지고는 딱 2개밖에 없었는데 C하고 H밖에 없었는데 그게 할로진을 집어넣거나 옥시즌을 집어넣는 것만 가지고도 굉장히 다양한 반응이 만들어져요. 자, 그걸 우리가 지금 공부를 하고 있는 건데, Then we used this kind of reagent, and this is very common proton source, and this is hydrogen atom or hydrogen radical. Do you remember? How could you make this hydrogen radical? Hmm? Homogeneous metallic breaking down. Right? That was the method that we used. And then the hydrogen was added to the double bond. The syn addition was made. And this one is we needed to have extra electron to the hydrogen. By the way, in terms of the electronegativity, hydrogen is close to the metal. Right? That's the first family on the periodic table. So very low temperature, hydrogen behave like a metal. Have you heard? Very, very low temperature, hydrogen, they behave like a metal. That means they tend to donate the electron, right? And then they have free electrons around. And now, how can you make this another hydride? You need to take electron, right? Then which is more electron donating the material than hydrogen? Those are metals, right? That's why those hydride reagents usually you use with the metal complex. So boron is metal, and a little bigger the metal on the same the column, that's aluminum, the peptide 3. And these guys donate the electron to make this hydrogen electron rich hydride. And aluminum is bigger than boron, so it has better electron donating the property. That's why aluminum hydride is more reactive than borohydride. And in addition to this, there is actually another count of the cation here, sodium or lithium. Seems like this is one reagent for it, the borohydride. And then this is the count cation outside. It may have low effect to this reagent, but actually it has some effect too. So last time I said, in this side, this is bigger inside here, this reagent, aluminum is more reactive than boron. But count cation wise, interestingly, it has the opposite effect. The smaller, it is more reactive. So out of 4 options here, sodium, lithium, boron, aluminum, and this is the strongest one out of 4. This is the most mildest one. Okay? So this is more reactive, the reducing reagent, hydride reagent. This is less reactive than this. Now, if you wanted to make this molecule, which reagent would you like to use? Here, reduction reaction happened here. Ketone was reduced into alcohol, and ester was not changed. If you choose out of here, which reagent would you like to use? This is a selective reaction, right? You don't want to touch this. You want to selectively reduce only one of them. Then it should be sodium borohydride. Then sodium borohydride, it can reduce aldehyde or ketone. Then if you want to reduce both of them, then you need to use a stronger one, lithium aluminum hydride. Okay. Lithium aluminum hydride can reduce ester. Now, if you wanted to reduce only this side, not touching this, what do you need to use? This is the ketone side. Ketone is more reactive. That's why milder sodium borohydride can reduce it, right? But if you wanted to reduce this part, what can you do? 지금까지 여러분들 배운 부분은 할 수 없어요. 약한 거 있으면 더 잘 되는 거 할 수 있고, 강한 거 있으면 둘 다 할 수 있고, 더 잘 되는 거를 막아놓고 이걸 하려고 하면 다른 팁이 필요합니다. 나중에 약간 배우겠습니다. Okay, now we can summarize here. If there is any reagent, the functional group aldehyde, we can use both of them. If it is ester, then you need to use the strong one, lithium aluminum hydride. Acid, also lithium aluminum hydride. Okay? 질문 없지? Clear? Okay, we just thought about the hydrogen as a reagent. Proton, H dot, and H minus hydride. How about the alkyl? Alkyl also we already have learned the carbocation in the last semester. Right? Carbocation could be generated as an intermediate for E1 reaction or SN1 reaction kind of things. Carbon radical. What do you think? How can you generate? This generation gives a lot of heat and pressure to simple molecules like a hydrocarbon. And selectivity is very poor. You don't know which bond will be cleaved. All bond is very similar to each other. Right? So those molecules are very boring. It has only CH. That's why after all the functional groups is introduced, organic chemists are kind of trying to find more challenging target. So that target is a CH activation. We want to functionalize the CH selectively. Of course, it's going to be quite challenging. So that's why it's kind of a new topic academically or the intellectually. It's more challenging. So selective CH activation is kind of the challenging the academic topic. Okay, usually we don't use this radical reaction for selective reaction. Then now, alkyl anion. So that's the option is we have learned halide and oxygen. Then carbon side is a delta plus positive charges. To make this negative, that's the reagent that we use using the metal again. So those metal, the typical example is using magnesium. And then Grignard reagent is that kind of reagent. So by adding magnesium inside here, this can provide one electron to R, so R minus, carbon anion. And then another one was given to the halide. So this kind of Grignard reagent can be made starting from alkyl halide. And using this, we can use this carbon nucleophile now. So far, those nucleophiles, with the alkyl halide, the nucleophile was a hydroxide. It is also the atomic nucleophile. Now, this is an example of carbon nucleophile, R minus or C minus. Then carbon nucleophile can attack here and then push up, and then this O minus is captured by proton. You know the notation here, right? 1 and 2. That means this reaction is stepwise. You add this reagent first, and then after the reaction is finished, then you add water. If you add this together, what happens? If you add acid to this reagent in one part, add it together, what happens? We have seen the example of Grignard reagent with alcohol. Even that break up this molecule, then what is generated? RH. Hydrocarbon is generated. That's not something you want. Usually this functional group addition is very expensive, and usually the time and money cost. So after you made that molecule, and then you don't want to break it up to give it back to just a simple oil. Yeah. So that's why you cannot mix together. Especially if there is an acid, then that reaction would be explosive reactions. So adding this one, and then very slowly you add the acid and quenching the reaction. So this is a two-step reactions like this. Okay, so this is the example of carbon-based nucleophile. And now you can make this kind of a carbon-carbon bond formation. Maybe this is the first example we are learning. And push up, and then the result is starting from carbonyl group, the product is alcohol. Like this. Now let's look at some examples. What product we expect? You have all the answers on your notebook, but try to think by looking at this. And attacking position is this. Delta minus here, delta plus here. Okay, this is attacking nucleophilic position. Carbon nucleophile. Attack this position and push it out, and then the end product is primary alcohol, adding one carbon and then alcohol. That's the product. How about this? Here this is the alkyl Grignard reagent. Interestingly, phenol also can be formed Grignard reagent. the starting material will be phenyl halide. Right? Phenyl halide usually the reactivity is not so good, but with metal, if you add it there, it can form Grignard reagent too. That means this becomes nucleophile. If you are not chemist, then by looking at here, 6-membered ring, 6-membered ring looks like almost the same. But we know now, benzene is quite special, the chemical, which is very stable, aromatic, but it can form Grignard reagent. That's very good to know. Then this guy attack here, aldehyde, and then this guy attack here, push it up. Then the product is, this guy is added here, and the product is alcohol. Okay, how about this? Methyl Grignard reagent, and then here's a ketone. Then this guy may attack, this negative charges may attack here, push it up, and OH is generated. This is formed. In the beginning, the starting material to product, maybe the shape is not familiar to you, that's why you need to practice. Okay. By looking at this, then you should be able to draw those product structure. Okay, practice a little further. So here, this is ester. Now you have a nucleophile. And if you look at here, it says 2. That means you need 2 equivalent of nucleophiles. Then, can you guess the product? Here, nucleophile is a methyl. Methyl anion, right? And this guy attack here first. And first the living group is this side will be pushed out. Then it generates intermediate ketone. Methyl 1, 2, 3, 4, butyl ketone. And second one, this come again and then push this up. And end product is alcohol. Is it primary, secondary, tertiary alcohol? What is it? It's tertiary. Now as end product you can see 2 methyl is added. That's why you need to have 2 Grignard reagents. Now, as a synthetic chemist, if you look at this, do you think it's possible to isolate just the ketone? If you use only one equivalent of the Grignard reagent, in principle it goes in, then it forms ketone as intermediate, right? If you use one equivalent of Grignard reagent, then can you make ketone? What do you think? What do you think? Possible? Not possible? If you say possible, then I will ask you why. If it's not possible, I will ask you then why. What do you think? Anybody has a good answer and reason? Do you remember when we learned about the sodium monohydride and lithium aluminum hydride? Which one was more reactive? Ketone and ester. Ketone was more reactive, right? That's why it reacted with milder sodium monohydride. That means intermediate ketone is more reactive than the ester. That's why even though it is formed very small amount, they will go further to the end product. Then, and the result will be, if you use one equivalent of this reagent, you will have mixture of half left here and half product. You will not get ketone as a product. Okay? Makes sense, right? How about this? This reaction, Grignard reagent, and then if you add that to carboxyl acid, if this reaction is using lithium aluminum hydride, then the reaction finished and it formed primary alcohol. Remember? Hydride attack. Ester and acid, both of them was finished in the reaction. And the product was a primary alcohol. But Grignard reagent, that is not so reactive. That reacts with the ester, but once it forms, first of all, this proton will react with this one first. And then it forms this hydrocarbon. Then second one can react, it cannot. So Grignard reagent, maybe the bulkiness over here, alkyl, compared to hydride or reactivity, is not as reactive as a lithium aluminum hydride, so the reaction doesn't go further. Okay? There's a big difference between hydride reaction and granite reaction. Hydride is a proton H minus, and in this case, alkyl anion. Alkyl anion cannot finish this reaction, so it's just a stop. This is almost like acid-base reaction. Mixed together, and only proton is captured, and you wasted one equivalent of a granite reaction, reagent, and finished. Reaction doesn't happen. Okay, to make this, you have several options. This is tertiary alcohol. You have a 1-methyl, ethyl, phenol. You have three options to use this, like this. You can choose any of those two to make these ketones. Even we just said phenyl group, phenyl granite reagent is also possible to form, right? So you have a full three options, any kind of ketones, and then using this granite reagent, and then you can make the same product. So if I give you the question, then okay, how will you make this molecule? Then you can design three different chemistry. Then your the consideration should be which reaction is the simplest and which reaction requires cheaper material here. That's more chemical engineering, the concept you need to use. Okay. So tertiary alcohol, you have this kind of options. Okay, here. Now to make this similar situation, to make this, then you have two options. Now two of them is equivalent. So that's why you have two options like this. Starting from this and using this the granite reagent, or starting from this and this. Which would you like to choose? If you are an engineer. The majority we are the chemists, but anyway, chemists also think economic the reactions. Which looks cheaper method? Granite reagent may be similar cost. You need to buy alkyl halide and then just adding the magnesium, then you can form the granite reagent. Right? How about this? Which one looks cheaper? Technically, this will be cheaper, right? As soon as we use as a solvent. Then, if you have option, then out of this, you may choose this. So this is already asymmetric, and to make this, you need to have another very sophisticated design of the reaction. Or definitely this will be the more expensive than this. So option can be this one. Okay, how about this? And the ester, acid doesn't work, we said, but ester, if you add this, take here, and then the second one take here, ester can finish the reaction. Just requires two equivalent of the reagent. Okay? One more time review. And this is some summary of how to prepare alcohols. Except this, we covered some of them, let's just say, starting from alkyl halide, using hydroxide as a reagent, essential reactions. Right? And ester or carboxylic acid, to make this, we could use hydride reagent, aluminum, lithium aluminum hydride, phenol, and alkene, we could do hydroxylation. Two ways, hydroboration and oxidation, or oxymercuration. Those were options to make the alcohol. And ketone, we could use, depending on the situations, hydride or granite reagent. Hydride, you just make it primary alcohol, or secondary alcohol in this case. With the granite reagent, you have the alkyl group 2, that will generate tertiary alcohol. Right? And aldehyde may be even the easier than ketone. So then we move on to reaction with alcohol. How to generate the alcohol is one direction that we studied, and from now on we move to alcohol reaction. So this reaction we talked last time. This reaction starting from alkyl halide using hydroxide, if it attack the can generate the alcohol. The reverse reaction may not be easy, we said, because the OH minus is not good leaving group. That's already very reactive compared to halide. Right? But there is some trick how you can make this OH as a good leaving group. that trick is you can make in acidic condition. In acidic condition, similar to water, hydroxyl group can abstract the proton and it becomes positively charged one. Then living group becomes water. Water is much better living group than hydroxide. So this is one trick. Especially if this is a tertiary alcohol, then it can form very stable tertiary carbocation. So maybe SN1 type of reaction is more preferred this way. If it has many alkyl group around, and that hydroxyl group in acidic condition, it has a good chance to be removed. Then the intermediate is a carbocation. Then you have options of E1 or SN1. Then either it can be substitution reaction or it can be elimination reaction. Right? So two reactions is possible. If it goes through this way, let's say this is SN1 reaction, how about the stereochemistry? Originally, let's say this is chiral R form. Okay? R form alcohol. And if it goes to this halogenation reaction through acidic condition, through SN1, what is this form? Is it S form or R form? If it's the same R form, we say retention. If it is a change it, we say conversion, the converted product, conversion. Right? What's the product ratio here? Is it R or S? 야, 이렇게 어려울 때 기회가 안 나? 아니면 겸손? 뭐 겸손한 척? If it is SN1 reaction, what happens? Conversion. Conversion. Retention. 둘 다 합니다. 모조리티가 이렇게 막 망설이고 있네. In SN1 reaction, carbocation is the intermediate. Carbocation is sp2, means it becomes planar. Then nucleophile can come either side, this side or this side. It generates a mixture of 50-50 of RNS. You lose the good information of a starting material here. You bought this chiral molecule should be much more expensive, and your end product is a racemic mixture, half and half. That's SN1. Okay? If it is SN2, you could expect conversion. Okay, this reaction. So another sophisticated method, not the acidic method. If you add ionic chloride, SOCl2, then this alcohol attack here, SOCl2 looks like this. Alcohol is not very good nucleophile. Alkoxide is good nucleophile, but still alcohol can attack. Like this. This can form reactive intermediate. After it forms the reactive intermediate, then this is formed by attacking here, and one chloride is pushed out. That chloride comes back and attack behind, and push out this good living group. Then it forms SO2, HCl, this is gas. It spreads out. That's why this is very good living group. So OH was not good living group in the beginning, but by reacting with this cyanide chloride, it becomes good living group. And even halide can attack from behind. This reaction is SN2 reaction. If it is a full SN2, then product is 100% converted. It's not SN1, right? It's a concerted reaction, SN2 reaction. Very similar reaction can happen with the PBr3. PBr3, again, same way. I hope the oxygen attack here first, and then one bromide pushed out. And that bromide can come back and attack from behind. Then push out the whole thing as a living group. So this is kind of activating hydroxyl group as a good living group. Okay? Hydroxyl itself is not good living group, except the condition of acidic condition. But in this case, very mild condition, very weak base, and this reaction can activate alcohol. and can be replaced by, reacted by this halide. Very sophisticated reaction. Okay, if you start with the alcohol of alcohol, the chiral one, okay, alcohol, at least you should be able to count this as R. Here, priority wise, this is the lowest one, 1, 2, 3. Right? Then rotation wise, this is to your side, and then this side, then this is the opposite, this is alpha. Okay. Then using this, PBr3 reaction, what product do you expect? Hydroxyl attack PBr3, and the Br coming back and attack, and then SN2 reactions. Your product will be IT halide is an alpha or S form. It should be S form because the one conversion happened. Okay. Now you have IT halide. Now here, if you add another nucleophile, let's say alkoxide or hydroxide, both of them may be possible. If you add alkoxide, if this reaction is also SN2 reaction, your product will be, this is nucleophile attack here, push it out. Product is ether. But anyway, that's not important. Is that R form or S form? If it is SN2 reaction, is that R form or S form? It's an R form because this is also converted one more time. So you come back to the original R form. And result wise, here this alcohol you could use as nucleophile. If you reacted with this ethyl bromide, then it could react with ethyl bromide, right? Then you could get the same product like this. Do you follow me? So we are talking about the nucleophilic addition reaction, a little more sophisticated version than last semester. And now we talk about the stereochemistry conversion. Okay? Originally alcohol, this is chiral center. And this one reacted with this, but Br came from the behind, converted this. That's why it becomes S form. Now this one reacted again with this, converted again. It went back to the original alcohol. Okay. Now how about this? Second reaction. Tosyl chloride. Have you heard or have you learned? 당연히 안 배웠다고 그랬지. 배워도 이해가 안 된다고 그랬지. 자, 토실 chloride, the reagent is like this. This is tosyl chloride. Tosyl is toluene sulfonyl chloride. This is very reactive species, and it can react with alcohol, react like this. Then this make with this oxygen and then with the third group, this becomes very, to hold together, tosylate is a good living group. Usually this is not the way we draw. Usually in the paper, usually we say TS. TS is a tosyl group. Okay. So tosylate is another way to activate the alcohol, to make the hydroxyl into good living group. Okay. Based on this, we will come back to this reaction. If you react with this alcohol with the tosyl chloride, then this alcohol attack here and then push out the chloride. And you have intermediate. Question is, what is the configuration of that intermediate? Is that alpha or S form? Is it R form or S form? R form Y. 누가 그랬어? 윤석을 했나? 준이가 그랬어? 왜 R form이야? This guy attacked this and pushed out the chloride. It looks like SN2 reaction. 다시 얘기해. SN1처럼 보였다. 이게 SN1처럼 보였다. So this attack here and this push out. Actually, this is not SN1, SN2 because this is a common center. Right? SN1, SN2 reaction is a nucleophilic reaction. That nucleus is a carbon nucleus. Right? So this is the attack here, then push it out. kind of replacement reaction, but it's not SN1 and SN2. That's not the main point here. Reaction product is like this. If you think about the reaction site, reaction center, the determining the center for chirality is this carbon, right? That carbon was not reacted. This oxygen attacked to the outside reagent, right? That means this chiral center configuration did not have a chance to be changed. Reaction happened to the outside, right? That's why this configuration, this C configuration is not changed. That's why this is originally alcohol and this intermediate is also alcohol. In comparison, in this case, this attacked this one first. The first reaction, PbR2 intermediate, is still same alcohol. But why it is converted? This bromide come behind and attack here and then push out the whole thing. That's why this intermediate becomes converted product as well. Okay? Tosyl case, only first step reaction finished. This hydroxyl attacked the tosyl and then tosylated here. Second step reaction did not happen yet. Here, if you add nucleophile, then this nucleophile come in and attack and push out, and this is converted. So it looks complicated a little, but actually it's not. In this case, only one step reaction and then one conversion happened. Here, looks like one step, but actually this is two steps. Alkoxy attacked this P, and then bromide attack, and then converted. So two step reactions. And conversion already happened here. That's why it becomes S. And then second conversion with the nucleophile attack again and coming back to it. Okay? So that's the difference of the reagent here. So this reagent can drive the whole reaction two steps. Activate and then nucleophile addition by bromide. Conversion one time. And then second conversion by second nucleophile. Here, this attack just intermediate, but conversion didn't happen. Just activation of alcohol. And one step addition here. 조금 복잡해 보이지만 잘 들여다보면 그렇게 어렵지는 않아. Okay, to make this, what can you do? We just said the Grignard reagent as carbon nucleophile. In this case, let me give you a hint. Cyanide is also carbon nucleophile. See, we wrote like this, but actually anion is here. This can act as a nucleophile. Then, to make this from this into this product, what do you need? What condition do you need? Two options, PbR3 or tosyl chloride. Then if you look at the stereochemistry, is that same stereochemistry? Let's come to this. This is ROS. R, because there's a 1, 2, 3, and then H is behind, so we rotate here 1, 2, 3 this way. This is alcohol. 지금부터 연습해서 stereochemistry 정확히 알도록 해야 돼. 자, 여기 볼까요? 여기는 1, 여기는 let's see, still 1 because CN is 1, and 2 and 3 rotated this way, but H is coming this way. That's why this is S. This is a converted. Okay, converted product. If you want to make this a converted product, then what reagent do you need to use? PbR3 or tosyl chloride? PbR3, R to R, R to S. Your nucleophile here is cyanide is here, and your end product was converted product. Then PbR3, you should use tosyl chloride because this is a true conversion. To make this opposite, the stereochemistry, you need to have one conversion. That's why you need to use tosyl chloride. Okay? 조금 복잡해 보이지만 몇 번 들다 보면 다 할 수 있어. Okay, next reaction. As we said, if this alcohol is a little hindered area with a lot of alkyl group, and acidic condition, okay, we can expect this can go to elimination. This elimination most likely you could generate the tertiary carbocation here, and then one proton is removed. If this carbocation is formed first, and then this proton donate, then what's the mechanism? SN1, SN2, E2, E1. So E1 SN1 is the common part, is the intermediate is a carbocation. That's E1 and SN1. SN2 is a concerted reaction. Nucleophile come in and convert, and then living group leaves. That's SN2. E2, we are looking at the again later. So in this reaction, then if you add the acid, then what product do you expect? Let's say carbocation is formed here, and then proton is removed, and several options. Maybe proton could be removed from this and generate this one or this one. So we learned something about carbocation stability wise. The tertiary is more stable than secondary, more stable than the primary, and end product wise, more substituents than less substituents double bond. This is a little more stable. Explanation can be done by carbocation stability or product stability. Product wise, more substituted 1, 2, 3 substituted this one 1, 2. So this is more stable than this one. Okay. Now in this case, if the water is removed first and then move to the next step, then this is the E1 mechanism. But this requires quite vigorous acidic condition, maybe a little softer reaction. Similar to PCl3 or PBr3, but this is the POCl3, it's a little different. P is oxidized, PO there. Then again, the hydroxyl group attack here first and push out the 1 chloride and form reactive intermediate. And this intermediate react with the base. Then this base come in and then take up this proton and then push this electron and push it out. This reaction is E2. SN1, SN2. The meaning of 1 and 2. 1 is mono species, 2 is a bimolecular reaction. Right? That's why SN2 reaction always nucleophile and this electrophile react at the same time. SN1, E1, carbocation forms first, and that is a rate determining step. That's why whether that's next step of nucleophile is a good nucleophile, bad nucleophile, it doesn't matter. The first step is more difficult and it's slower. That's why next part is very fast. E2 reaction is also two species react together. That species is this guy. Comparing to SN2 reaction, SN2 case the partner was a nucleophile, and then that attacked this position directly. That's nucleophilic addition. E2 is elimination, and reaction site is not this carbon center. That's next position proton. This reacted with the proton, that's why this is not called as a nucleophile. That is called as a base. Okay. Sometimes base nucleophile can be same species, but depending on those end product, if it forms elimination product, then we call it base. If it forms reacted here, then we call it nucleophile. Okay. So this is E2 reaction. Attack here and here, like this. This is conservatively happening. Electron push this way, this is pushed back and pushed back. Okay. This is E2 reaction. Hopefully this is good review for the reaction. How about this? Starting from the carboxyl acid, if you want to make the ester, actually this one we may learn it several weeks later. But one of this common way is you can use acidic condition, dehydrating acidic condition, remove water, and then you can form this. But a little more sophisticated method is similar to alcohol activation. In alcohol activation, one method was tosyl chloride or thionyl chloride. Then it can form chloride reagent. And in similar way, carboxylate can be also the nucleophile attack this thionyl chloride and it can form this kind of activated acid halide. We are going to touch very briefly here. We will learn it again several weeks later. And then if you use a nucleophile, very mild nucleophile can attack here and push out this chloride and you can form ester 2. Okay, just a touch of it. Now, oxidation reaction wise. Primary alcohol, if you oxidize it, first the product is aldehyde. And then carboxylate, like ethanol. Right? Ethanol can form acetaldehyde and then acetic acid as the product. Secondary alcohol, once oxidized, then there is no further position to be oxidized, so ketone is the final product. Tertiary alcohol, it cannot be oxidized. There is no proton to lose, so it just stops here. Oxidation doesn't happen. How about this? In this case, oxidizing reagent, like the chromium or the trioxide, strong oxidant, then usually it doesn't stop, it just goes further. Aldehyde and the finally acid. If it is the primary alcohol, you have these options. The mechanism is like this. This oxygen will attack here, and then base come back and push and then generate this one. Among these reactions, which step is really oxidation reaction happens? Step 1, step 2, step 3. Sorry, step 1, step 2, step 3, step 4. Oxidation reduction happens where? One, two, three. Oxidation reduction is the electron donating step, right? Which is that? As a whole reaction, which one is oxidized? This carbon was oxidized, right? Then this is the oxidizing reagent. Then which one is reduced? Chrome is reduced. Originally this was a +6. Now it ended as a +4. That is reduced. Then you can look at when that chrome is reduced here. This step. Pushing this electron is donated to the chrome. This step is oxidation reduction happens. Okay. Oxidation reduction is electron donating and accepting permanently. That's oxidation reduction. Right? Acid base is temporarily just pretend to give, but it doesn't fully give. Just disturb the partner's electron structure. Okay. So similar way, this is also a very strong reagent. Polychromate, the chromate or the dichromate, these reagents are strong and the oxidizing reagent. So if it has primary alcohol, it will push to the carboxylic acid 2. But if it is secondary alcohol, no further options. After the first step of the oxidation, ketone stopped. Now, if you want to stop the reaction, I don't want to make an acid. I want to generate the aldehyde. I want to stop in the middle. What is your option? Lithium aluminum aldehyde, sodium boroaldehyde. If you need a selective reagent, then a little mild reaction. Mild reagent. You may not learn this. That reagent, what we call, is the person's name, chemist's name. That's the Martin. They generated this kind of reagent. And this Martin as a reagent can stop the reaction at the stage of aldehyde. Okay. Now here again, the oxide, the reducing part is this iodide. And this iodide is also changed into this. This +2 means 2 electrons is accepted to this. And oxidized by taking up 2 electrons out of here. And end product is chromium reagent, is a very strong oxidant. They can push the reaction to the end. Ketone or carboxylic acid. But this Martin reagent is can stop the product at the stage of aldehyde. Now let's think about this reagent with the magnesium, the reagent. To make the Grignard reagent. We hope that to add this magnesium inside here, MgBr, then it becomes Grignard reagent. The problem is the reagent has a hydroxy group, and that means it has a proton. Even though this product is made, then that reacts with this proton very quickly, and then it will be destroyed here. That's why this reaction cannot happen. Grignard reagent does not form. You just waste your material. Means this is similar to mixing sodium metal with the water. Right? Sodium with the alcohol, problem. Magnesium with the alcohol, also problem. That means it reacts with this one first. That's a problem. Right? So Grignard reagent is very useful, but if it has a special functional group, then even though you have an alkyl halide, making Grignard reagent is time to time very difficult. For example, if it has any kind of proton source, it's a problem. Right? It reacts with the proton first. Or if it has target of a Grignard reagent, we just learned so far, Grignard reagent can react with the aldehyde, ketone, ester. Right? Then the molecule itself has this kind of functional group. Then as soon as this Grignard reagent is formed, then it can attack that position, self-reactions, before it reacts with another factors. So Grignard reagent, to make a Grignard reagent, somehow you need to control these extra functional groups. So for that, the concept of protecting group. Hydroxyl is a problem, then why don't you just block the hydroxyl group? And the typical reagent is trimethyl chloride. And this is similar to tri-T-butyl chloride. Right? Just the carbon is exchanged with the silicon. With this reagent, if you add alcohol, then we can induce this reaction and block this oxygen. This reaction we call protection. And this one looks like this is like SN2 reaction, right? SN2 reaction. But if it is a T-butyl chloride, SN2 reaction happens? No, that's a tertiary halide. It's very crowded. It cannot attack. But in this case, the silicon is much bigger. Silicon is much bigger than the carbon. So carbon-carbon bond is about 1.5 Ohm long. Silicon is almost 2 Ohm long. That's why it allows the protections. Then once it is attacked here, similar way, by this attack here, and then it can protect these hydroxyl groups. So this kind of a strategy we call protecting group strategies. Then this the intermediate does not have any kind of the proton source, so it can be safely react for the next step. To deprotect by adding acid and then the water, then it can remove this silicon bond and it can regenerate this hydroxyl groups. Then how to use this? This reagent, originally you cannot generate the Grignard reagent, but now you can do. You have a hydroxyl. You wanted to make Grignard reaction here. Then first step is you react this hydroxyl group with the silicon and protect. Then you generate Grignard reagent and do the reaction, and with some aldehyde, and it forms the alcohol. Now we generate the alcohol. This is already finished the reaction. That's fine. And then you deprotect this silicon group, and then we generate two alcohols. This is the strategy. So to summarize, hydroxyl group, if you want to use it as a leaving group, you activate it by thionyl chloride or PBr3. That reagent converted alcohol into halide by conversion. SN2 reaction was involved there. Another method was a tosyl chloride, low conversion, because the oxygen was reacting with the deactivated group. Right? And then you can use any kind of nucleophile behind, and then end result will be one conversion. Okay, we have learned a little about the last week. This kind of the electrophilic aromatic substitution, and then hydroxyl is electron donating group, and then it's activating and then directing wise also and para position activating. Right? And if you oxidize this phenol, single phenol, now to oxidize this one, you need to have a CO double bond here. But because of this aromatic ring, you cannot generate the CO double bond 1. That's why it catch out another oxygen, and then end product is 1,4-diol of the phenol structure is the product. If you have a phenol oxidized with a strong deoxidizing reagent, and the product is a diol. Okay. This diol you could reduce back or oxidized. You can count whether this is really oxidized or not. You will figure out. So beta-quinone is oxidized form. This hydroxyquinone is a reduced form of this. Even though you started with a single oxygen, the product will be dioxygen product. Single oxygen cannot be oxidized and then can form the stable product. Okay, let's just skip this. Let's finish. In IR, IR usually gives you the information about the functional group. Right? The typical functional group we didn't know yet. Carbon group 170, 1700 or 1800 here, and a lot of CH bound here. Now, OH group we are learning now. OH group generate strong peaks around the 3000, above 3000 area. OH, water, alcohol, phenol, as almost not distinguishable, and also concentration dependent. So not much information you can get. Just a broad peak here you see above 3000 there is OH group or even NH group, a proton source. That is the signal of this. A little information of a benzene ring, but this is also overlapped with the double bond. Not much information. Carbon NMR, to summarize quickly, if it doesn't have anything, just a simple alkyl group about the 30, 40 ppm. With a one heteroatom, maybe 70, 60, 70 range. Okay, so the quick review. Proton NMR, if there is a directly connected to the alkyl group around 1 or 2. And one heteroatom around the 3 and 4. And by those coupling pattern, you can figure out which one is which. This is the propanol, and this one will interact with this. It may form quadruplet. Oops. It may form triplet because of this two. N plus 1. Right? And this one also triplet like this. And then this one is because of this quadruplet and triplet, quadruplet by triplet. Okay. And a little complicated like this. 이런 NMR 스타트는 나중에 계속 나올 때마다 조금씩 리뷰할게요. If you add any deuterated solvent, then proton is exchanging quickly. So in deuterated solvent D2O, then exchange quickly, so you may not see this proton. Protic proton can be quickly exchanged, so you can suppress. You don't see that in NMR. You just see water. Okay, there's some summary, but I think we can finish here. This one you can see. Let's do very quickly. This reaction, what do you get? Primary alcohol, right? Hydride is attack here and then push out and then protonate. Ketone? Secondary alcohol, just a push out and then same way. Ester? One react here, push out, and then second one react here, push out. Two hydride unit, and then that's also primary alcohol. Two hydride was added. Acid? No reaction, no reaction. Sodium borohydride, no reaction. Lithium aluminum hydride, that react in this case. No reaction was a Grignard reagent. Was no reaction. Same product you could get. Grignard reagent attack. One added, and formaldehyde is a primary other alcohol you can form. Attack here and push out. One reagent. Aldehyde. Can form, attack here, and also this is secondary alcohol. ketone, 1 alkyl, 2 alkyl, 3rd alkyl, but here, tertiary alcohol, you will get ester. I'll take here first, and then this is removed first, and then add another one and push up. So that secondary or tertiary? You added two reagents of this. One added here, push out. Second one added tertiary. The carboxylate with the Grignard reaction, no reaction. This doesn't work. Just a finish up, just a change without this proton, with this. No product. Dehydration will be formed as elimination. Can be either E1 or E2. This is a mild reagent. This attack here first, and then base catch up here. Most likely this is a E2. Okay, mild reaction because it doesn't form carbocation intermediate. Okay. Oxidation, strong oxidant, chromium oxide or dichromate. They are strong oxidant. Finish up to the end, carboxylate. Okay. And to make this stop in the aldehyde state, what do you need? Somebody's name. That's Martin reagent can finish up this reaction at aldehyde state. And that's Martin reagent here. What does this mean? Oxidation. Okay. If it's the secondary of the alcohol, that's Martin also can work to start the ketone. To make a ketone, you have two options there: chromium reagent or that's Martin. Either way is fine. Both of them can finish, can start the reaction in ketone. Phenol, if you oxidize, what do you get? It's a diphenol is the product, not single ketone. Single ketone then you cannot make up this the aromaticity or the bond of this. In this case, looks like this is a dehydration reaction, but product-wise, this was formed. What was migrated? Proton was migrated. In this case, methyl was migrated on this. Okay. Proton migration is much more common, but if there is no other option, this is positive charge, then one methyl group migrated and finish up the migration. Okay. Okay, so this is the summary of today's class. So next class will be next Tuesday, and assignment I will give out. And next week we will continue the oxygen containing materials, ether, hydroxide, a little about the silent containing one. After that, we will take the first revision. Okay, if you have any question, then